Good afternoon and welcome to our second differential equations lesson. Today we're going to finish chapter 1 by talking about classification, and then we will start chapter 2. Linear equations, separable equations, and then we will discuss some differences between linear and nonlinear equations. Our first topic is classification of differential equations. First, I want to discuss ordinary differential equations. If a differential equation only has ordinary derivatives, in other words, something like dv dt or dp dt, then it's called an ordinary differential equation. And instead of writing ordinary differential equation each time, I'm going to use the common abbreviation ODE. Anytime you see ODE, just think of it as differential equation. Almost all of the differential equations in this course are ordinary differential equations. So anytime you see ODE, it just means differential equation. For example, the two differential equations we looked at last week, the falling object equation and the mice and owls equation. These are ordinary differential equations because the derivative is an ordinary derivative. There's another type of differential equation called a PDE, or partial differential equation. If the derivatives in the differential equation are partial derivatives, then the differential equation is called a partial differential equation, or PDE. We will see a small amount of PDEs in this course, but mostly we're going to be talking about ODEs. In the final chapter of this course, the final 3 weeks, we're going to be talking about systems of equations. If there's only one function that we want to find, then one differential equation is enough. But sometimes there are two or more functions that we want to find, and then we need a system of differential equations. For example, this is a system of differential equations. We have two functions, a function x and a function y. And notice that in each equation, both x and y appear. We can't find one function first and then find the second function. We have to find both functions at the same time. When we come to this final chapter, we're going to need to use quite a bit of linear algebra. We'll need to use matrices, eigenvalues, eigenvectors, linear independence, etc. So when we come to this point, I will suggest that you revise your linear algebra notes. The order of a differential equation is the order of the highest derivative in that equation. For example, the falling object equation and the mice and owls equation are both first order ODEs. This equation, we look at how many derivatives we have. There's 0 derivatives of y just here, 1 derivative of y just here, and 2 derivatives of y. From 0, 1, and 2, what is the biggest number? The biggest number is 2. This is called a second order ordinary differential equation. This equation has 3 derivatives of y, 2 derivatives of y, 1 derivative of y, and 0 derivatives of y. The biggest derivative is the third order derivative, so this is a third order differential equation. We can also classify differential equations into linear and nonlinear equations. This concept should be familiar to you from your linear algebra course. A differential equation is called linear if, in this case, capital F is a linear function of y and the derivatives of y. Important point to note here is we don't care about t. We don't care if we have a linear function of t or if it's not a linear function of t. We don't care. We're only looking at y and derivatives. So in other words, we're looking at something like this. First of all, a0t, this could be any function of t. We don't care. Linear function, non-linear function, we don't care. But then there's just one y term. In this case, the nth derivative of y. And then plus some derivative of t, just any function, doesn't matter. And then there's just one y. This is not y squared, it's not cos y or e to the power y, it's just y. And then we go all of the way along. Each of the terms between the plus signs is just some function of t multiplied by a y is equal to some function of t. We might want to cross out the t terms to understand it. So let's suppose we cross out everything involving t. Just ignore, just pretend they're not there. And let's cross out all of the derivatives of y. Then what we're left with is y plus y plus y plus y, etc. If we can do this, then we have a linear equation. If our differential equation doesn't look like this, then it's not linear. We say that it is non-linear. For example, y triple prime plus 2e to the ty double prime plus y prime is equal to t to the power 4. We have a problem here in this final term. We have y multiplied by y prime. That's not just one y on its own, it's y multiplied by y. So this equation is non-linear. Let me go through some examples. I'm going to show you some differential equations, and I'm interested in, is each equation linear or non-linear, and what is the order of the differential equation? And I'll go slowly so that you can take a mental note, try to understand what the answer is before I reveal it. 3 derivatives of y plus 2 multiplied by 5 derivatives of y plus a derivative of y minus e to the t d squared y dx squared is equal to 0. First of all, what is the order of this equation? We look for the biggest derivative. The biggest derivative is 5, so this is a 5th order equation. And then we look to see, is this equation linear or non-linear? If I remove all the derivatives, all the numbers, all functions of t, then what are we left with? Then we're left with y plus y minus y is equal to 0. All of the y's are separated by plus signs or equal signs, so this is a linear equation. This equation is 5th order and linear. Another one, think about this one. What is the order of this equation? Is this equation linear or non-linear? This equation is 3rd order. The largest derivative is 3rd order derivative. And it's non-linear because we have cos of dy dx. Cos is not a straight line, cos is not a function, therefore this equation is not linear. This is a non-linear equation. d cubed y dx cubed plus cos of x dy dx is equal to sine x. Same question, linear or non-linear, what is the order? This equation is third order and linear. It's third order because the highest derivative is 3. If we do my trick of crossing out all of the derivatives, cross out all of the derivatives, and then cross out every function of x, so cross out the cos x, cross out the sin x, what are we left with? We're left with y plus y is equal to 0. So this is a linear equation. Y double prime minus y squared is equal to x squared. How to think about this equation? Is the order, is this or non-linear? Correct, this is second order non-linear. And I think this is the final one. E to the power x, 7 derivatives of y, minus x cubed, 99 derivatives of y, plus 2x to the power x, y triple prime, minus x squared, e to the power sine x is equal to 2020. Yes, this is the 9th order, and this equation is linear. That's the end of chapter 1. Next, I want to talk. Yes, let me talk about this one. Y double prime minus y squared is equal to x squared. This is second order, of course, because we have 2 derivatives of y. We might wonder, why is this equation non-linear? Cross out all of the derivatives of y, so cross out the double prime, and then cross out every function of x. Cross out the x squared. And then what do we have left? Do I have y plus y 0 or y minus y is equal to 0? The answer is no. We have y squared. If we draw the graph of y squared, y against y squared, looks like this. Is this a straight line? The answer is no. This is not a straight line. Therefore, this equation is not linear. If I go back. This is the equation of a linear equation. We have to have one y, a derivative of y, but that's all. There's no y squared, it's not sine y, it's just a 1y. And then a 1y, and so on. 1y just here. And then other than that, we have functions of t. And there's no functions of y, there's no y squared, there's no sine y. Nothing complicated, it's just a derivative of y, a derivative of y, a derivative of y, and plus functions of t. I hope that's clear. If not, ask me again at the end of the lesson. Chapter 2 is about first order differential equations. In this chapter, we're going to be looking at differential equations like this. We're going to have one function of y is equal to some function of t and y. We're going to look at different types of first order equation. The first type of equation we're going to look at is linear first order ordinary differential equations. So we have dy dt is f of t and y. If f is a linear function of y, and I remind you, we don't care about t, we only care about y. If this is a linear function of y, then this equation is a first order linear ODE. Last week we talked about equations like this. Dy dt is equal to minus ay plus b for some numbers a and b. This week we're going to make this a little bit more complicated. We're going to be looking at dy dt plus p of ty is equal to g of t, where now instead of numbers a and b, we're going to eventually get to functions p and g. Let me remind you how we solved the equation last week. Starting with dy dt is minus ay plus b, we wanted to separate the variables. The dt we moved up to the right by multiplying both sides by dt, and then on the left we move y minus b minus a over here by dividing both sides by y minus b over a, and then we're left with minus a on the right. If we can do this, if we can separate all of the y terms on the left, all of the t terms on the right, then we're allowed to integrate. If we can't separate variables like this, then integrating will not work. This only works if all of the y terms on the left and all of the t terms on the right. Then we calculate the integral. Natural logarithm of the absolute value of y minus b over a is equal to minus at plus some constant c. And then using the method we discussed last week, and which we will repeat later today, we've rearranged this to the form y is equal to b over a plus a different constant, small c, e to the minus 80. Remember this answer, we'll come back to this. So, for example, if I have the equation dy dt plus 2y is equal to 3, then here a is 2 and b is 3, then the solution is 3 over 2 plus some constant c e to the minus 2t. Unfortunately, this method can't be used if we have functions p and q. So we need to discuss a new method. And the method I'm going to talk about now comes from Leibniz. This is the idea. First, to find a special function, which we call an integrating factor. Then we multiply our differential equation by this integrating factor. And then step 3, we're going to integrate. Let me repeat again. Step 1, we need to find a special function. Step 2, we multiply our equation by the special function. And then step 3, we're going to integrate. For example, use an integrating factor to solve dy dt plus 2y is equal to 3. We've just solved this equation using a different method, so we know the answer. Using the method of Leibniz, we're going to solve this, and you will see that we get the same answer. Then we'll use this method on more difficult equations. The first thing we want to do is we want to find this special integrating factor. But so far I haven't told you how to find it. So let's suppose at this point we don't know what the integrating factor would be. Let's suppose we move on to step 2 and we multiply our differential equation by mu t. dy dt plus 2y is equal to 3, multiply this by mu t dy dt plus 2 mu ty is equal to 3 mu t. And then the question is, how do we find this special function mu t so that the left side of this equation is integrable? Notice this. Notice that if I take the derivative of mu t multiplied by y, using the product rule, I get mu t dy dt plus d dt y. And this is kind of similar to what we have. We have mu t dy dt in both of these. And then on the right, on the second term, I have 2 mu ty and d mu dt y. I want these to be the same. So in other words, I want d mu dt to be the same as 2 mu. We want to choose the integrating factor mu such that the derivative of mu is equal to 2 mu. But we know how to solve this equation. We can use the method from last week. What we do is we separate the variables, all of the mu terms onto the left, all of the t terms onto the right, and we integrate. And you can check this when you have a free moment. We find some constant c e to the power 2t. Now, we could choose any value for c that we want. So, for example, I might choose c as 15, 10, 20, 20. Just choose a silly number if I wanted to. This would give us a correct answer if I chose that c is 15,102,020. But really, I like easy numbers. So I'm going to choose c equal to 1. That will give me a nice, easy function, e to the power 2t. If I can repeat this, we don't need to find every mu that works. We only need to find one of them which works. So we could choose any value of c, but not 0 that we wanted. I like easy numbers, so I choose c is equal to 1. So go back to our differential equation. We started with dy dt plus 2y is equal to 3, and then multiplying by the integrating factor, which we now know is e to the 2t. Get e to the 2t dy dt plus 2e to the 2ty is equal to 3e to the 2t. Because we've chosen the correct integrating factor, we can now use the product rule to write the left side of this equation as just the derivative of e to the 2ty. You can check this is the same as e to the 2t dy dt plus 2e to the 2ty by the product rule. And now we've simplified our equation. Now we have a derivative of e to the 2ty and 3e to the 2t. Both of these are easy to integrate. If we integrate derivative, the integral of the left side is just e to the 2ty, and if we integrate the right side, integral of 3e to the 2t dt gives us 3 over 2 e to the 2t, and then of course when we integrate we have to add a constant, plus c. Divide by e to the 2t and we get the solution 3 over 2 plus c e to the minus 2t, which is the same solution that we found using the method from last week. Now, note that for the equation dy dt plus 2y is equal to 3, we've found that we want the integrating factor e to the power 2t. Let's do another one, or at least we could another one. Use an integrating factor to solve dy dt plus ay is equal to b. Now we have a number a just here. And if we repeated everything that we did in the previous example, and I'll leave this for you to check, you can go through this method if you wish, you will find that the integrating factor we want is e to the power 80. Let me move on. Let me make this a little bit more difficult now. Now let's suppose instead of some number b, we have a function gt. Solve dy dt plus ay is equal to gt. The integrating factor doesn't depend on b or g. It only depends on the coefficient of y. In other words, it only depends on this a. So again, we're going to use e to the power 80. So we take our differential equation and we multiply by e to the power 80. To get e to the power 80 dy dt plus a e to the 80y equal to e to the 80 gt. And you will notice that because we've chosen the correct integrating factor, we can use the product rule on the left side to write this as just the derivative of, there's a make here, e to the power 80 y. This should be e to the power 80. And then we can integrate. Integrate the left side, of course we just get e to the 80y. And on the right side we get the integral of e to the a. I'm changing variable s, gs, ds, and then put t in. I'm being a little bit careful here because we have a variable t outside an integral and I need a dummy variable inside an integral. I'm changing that to s, but that's all. Don't worry about this. And then divide by e to the 80 to get the solution. E to the power minus 80, integral, and then after we calculate the integral, we're going to put t in. E to the power a, dummy variable s, g of dummy variable s, ds, plus c e to the minus 80. For example, solve dy dt plus a half y is equal to 2 plus t with the initial condition y of 0 is equal to 2. First, we're going to find the solution to the differential equation, and then we're going to need to choose the constant so that the initial condition is also satisfied. And notice the number here we have is 1/2. This tells us our integrating factor must be e to the power 1/2t. So we're going to multiply the differential equation by e to the power of 1/2t, or e to the power of t over 2. Let's get this. And then we use the product rule to write the left side in an easier form. We have d dt of e to the power of t over 2y is equal to 2 e to the power of t over 2 plus t e to the power of t over 2. And then we integrate. Left side is easy. Integral of a derivative, the derivative just disappears, and we have e to the power t of 2y. And then we need to integrate the right side. Integral of 2e to the t over 2 is easy, just 4e to the t over 2. For the second term, we're going to do integration by parts. I mean, this formula, which you saw in first year calculus, integral of u dv dt is uv minus the integral of du dtv. If you check this when you rewatch the lesson or when you read the lecture notes, you can check that when we integrate this, we get 2t e to the t over 2 minus 4e to the t over 2. And then this simplifies to just 2t e to the t over 2, some constants. Divide by e to the t over 2, and we get the general solution to the differential equation, 2t plus c e to the minus t over 2. The final step is to find the value of this constant c to satisfy the initial condition. I want to satisfy y0 is equal to 2. When we put t in, we get 0 plus c, and we can see straight away that c must be 2. So that gives us our solution, 2t plus 2e to the minus t over 2. Next example, solve dy dt minus 2y is equal to 4 minus t. I'm not going to do this full example, but I'm going to tell you the answer, and then I'm going to ask you to check that this is correct. We have the number minus 2 here, so our integrating is going to be e to the power minus 2t. When we use our method, multiply by the integrating factor, then use the product rule, and then integrate. You can check that the answer is minus 7 over 4 plus t over 2 plus c e to the power 2t. Now let's make this more difficult again. Now let's suppose that instead of a number in front of the y, we have some function p of t. We need to know what integrating factor do we use for equations like this. And let me warn you, a mistake that a lot of students in past years have made. The integrating factor for this equation is not e to the power p, as I'm going to explain. We'll start the same way that we did before. We don't know mu t yet, so we're going to move on to the next step. We're going to multiply our differential equation by some unknown function mu. Mu dy dt plus p mu y is equal to mu g. As before, the left-hand side looks like this. I have mu dy dt in both equations, and in the second term I have pt mu y and d mu d dy. I want these to be the same, so I want to have d mu dt is p of t mu. As before, we know how to solve this equation. We can solve this by separating the variables and then integrating. And when we do this method, when we move all of the y terms to the left, all of the t terms to the right, and then integrate, I'm skipping it, I'll leave this for you to check. We get some constant c, and then the exponential of the integral of p. We could choose any value of c that we want, as long as c is not 0. Because I like easy numbers, I'm going to choose c is equal to 1. And then I get that mu is the exponential of the integral of p, or to write it a different way, e to the power integral of pt dt. So as I said, the integrating factor is not e to the power pt, in fact, it's e to the power integral of pt. Then, because we have the correct integrating factor, we can use the product rule to write our differential equation as the derivative of mu y is equal to mu g. We can integrate and then we can rearrange to find a general formula for the solution. But in practice, we don't use this formula. In practice, we solve each example using its own equations. For example, solve ty prime plus 2y is equal to 4t squared. Now, we know how to solve y prime is equal to p of t, y is equal to g of t now. But we don't have this, we have an extra t at the start. The first thing to do is to change our differential equation so that it looks like y prime plus pty is equal to gt. And we can do this by dividing by t. Assuming t is not 0, we can write our equation of the form dy dt plus 2 over ty is equal to 40. Now we have pt is equal to 2 over t, and for gt we have 40. We need to calculate the integrating factor. Remember, mu t is e to the power integral of pt, which for this equation is the exponential of the integral of 2 over t dt. The integral of 2 over t is 2 natural logarithm of the absolute value of t. And then rearrange this, we just get t squared. We are going to use the integrating factor, mu is equal to t squared. We're going to multiply our equation by t squared. First of all, ignore this. We'll try again. So our differential equation was dy dt plus 2 divided by ty is equal to 40. And we multiply by t squared to get t squared dy dt plus 2ty is equal to 4t cubed. And because we've chosen the correct integrating factor, we can use the product rule to write the left-hand side as d dt of t squared y. We can integrate this derivative of the integral of the derivative of t squared y is straightforward, which is t squared y, and that's equal to the integral of 4t cubed, which of course is just t to the power of 4. And then of course plus c. Divide by t squared to get the general solution to the differential equation. T squared plus c divided by t squared. But remember, we're not solving just a differential equation, we're solving an initial value problem. We also want to have y of 1 is equal to 2. To make this true, we must choose c is equal to 1. That gives us our solution, t squared plus 1 over t squared. And remember I said we're doing this assuming that t is not equal to 0. Because we're starting at t equal to 1, we must have, this is valid for positive values of t. The graph looks like this. Every one of the blue curves is the solution to the differential equation. Every one of these blue curves is t squared plus c divided by t squared for some value of c. For example, if I choose c is equal to 0, we just get t squared, which is, of course, this curve. We wanted to use c such that y of 1 is equal to 2. In other words, so that we pass through the point where x is equal to 1 and y is equal to 2. In other words, we want the curve which passes through the point 1, 2. This red line is the solution to our initial value problem. Now, note that this solution is a differential function which is defined on the open interval from 0 to infinity. We can note that the solution becomes unbounded and asymptotic to the y-axis as t decreases to 0. This notation, t decreases to 0, is the same as saying t tends to 0 from the right, which is a notation Thomas Calculus uses. I prefer this notation. This makes more sense to me. T goes to 0 and t decreases to 0. It makes more sense to me than writing 0 plus. Why does this happen? This happens because our function pt, which if you recall was equal to 2 divided by t, this function has a discontinuity at t equal to 0, so our solution became unbounded and had a discontinuity at t equal to 0. Also note that the function t squared plus 1 over t squared for t less than 0 is not part of the solution to our initial value problem. The solution to our initial value problem is only defined between 0 and infinity. So any functions on the left half of the graph on the other side of a discontinuity are not included. When we get to a discontinuity, we stop. Something else we can note. Forgetting the initial value problem for a moment, just thinking about all of the solutions to differential equation. If c is positive, then solutions are asymptotic to the positive y-axis as t decreases to 0. But if c is less than 0, then the solutions are asymptotic to the negative y-axis as t decreases to 0. I'm going to go back to the graph. What I mean is these curves go up as we decrease to 0, whereas these curves are going down to minus infinity as t decreases to 0. The behavior is changing. And the behavior changes at the initial value y1 is equal to 0. This value where the behavior changes is called a critical initial value. In first year calculus, you learned about critical points where derivatives change. For differential equations, we have critical initial values where the behavior changes. So before I go on, let me revise very quickly. If we're solving y prime plus ay is equal to something, gt say, the integrating factor we want to use is mu is equal to 80. If instead of a we have a function, let's suppose we have y prime plus pt, y is equal to gt, then our integrating factor that we need to use is mu is equal to e to the power integral of p. And you will note that these are actually the same formula. If pt is equal to a. If pt is equal to a, then we would have e to the power of the integral of a. Where can I write it up here? If we did e to the power integral of a dt, then we would just get e to the power 80 plus a constant, but we don't need a constant. So these are the same formula in the special case where pt is a constant. The second type of first order equation I want to look at is separable equations. The general first order differential equation, dy dx is equal to some function f of x and y. Now instead of using t as the independent variable, I'm using x, but other than that it's the same. Yes, we can take a 10-minute break and then we can finish the lesson if you wish. It means that we would delay later. Would anybody else like to take a break? Okay, in that case, I'm going to take a 10-minute break. And I'll start at 2 minutes past 2. Nice. Okay, let's continue. I need another 20 or 30 minutes to finish today's lesson. I want to talk about separable equations, and we're going to be re-talking about the method from last week. In section 2.1, we looked at linear equations. We're going to study another special type of equation called separable equations. The general first-order equation could always be written in the form some function m of x and y plus some function n of x and y dy dx is equal to 0. There's an easy way to do this. We could always write m is minus f, and we could write n equal to 1. But of course, there's many different ways we might rearrange this. Sometimes it's possible to rearrange this so that we have a function of m, which is a function only of x, plus the function of n, only of y, dy dx is equal to 0. If we can do this, if it's possible to rearrange this equation so that it looks like this, then the equation is called a separable equation. The first order ordinary differential equation is called separable if we can write it as some function m of x, notice only x here, there's no y, plus some function n of only y, dy dx is equal to 0. Note that if we have mx plus ny dy dx equal to 0, we can rearrange this so that all of the x terms are on the left and all of the y terms are on the right. In other words, it's possible to separate the variables. Hence the name separable equation. For example, consider dy dx is equal to x squared divided by 1 minus y squared. First, show that this differential equation is separable, and then solve this differential equation. The first thing to note is the 1 minus y squared. We can move over to the left and multiply both sides by 1 minus y squared, and then we can subtract x squared from both sides to get minus x squared plus 1 minus y squared dy dx is equal to 0. We have only x terms plus only y terms, dy dx is equal to 0. So this differential equation is a separable differential equation. How do we solve this? Well, notice these two things first. Notice that the derivative of minus 1/3 x cubed is minus x squared, and the derivative of y minus 1/3 y cubed with respect to y is 1 minus y squared. So in other words, our differential equation is the same as derivative of minus 1/3 x cubed plus the derivative of y minus 1/3 y cubed dy dx is equal to 0. We can simplify this further using the chain rule. Recall that the chain rule says, let's say, dz dx is equal to dz dy dx. And that's the sort of thing we have here. dy of some function dy dx. This is the same as dz dx. Using the chain rule, this is the same as d dx of minus 1/3 x cubed. In other words, the first term is the same. And then using the chain rule on the second term, instead of d dy, we have d dx of this function. Or we could write this as all one piece. D dx of this function is equal to 0. If the derivative of a function is equal to 0, then that function must be constant. In other words, minus 1/3 x cubed plus 1 minus 1/3 y cubed must be equal to some constant, let's say capital C. And we can rearrange this slightly, just multiply by minus 3 to get x cubed minus 3y squared plus y cubed is equal to, and it would be minus 3 capital C. But capital C is just some number which we don't know. So minus 3 capital C is some number we don't know. We can give this a new name. We can call this small c. The solution to this differential equation we can write as x cubed minus 3y plus y cubed is equal to c. This same method can be used to solve any separable equation. For example, consider the general separable equation, mx plus ny, y prime is equal to 0. And let's suppose that we know two functions, h1 and h2, such that the derivative of h1 is equal to m and the derivative of h2 is equal to n. In other words, let's suppose it's possible to integrate m and it's possible to integrate n. Then our differential equation becomes derivative of h1 plus derivative of h2 dy dx is equal to 0. Or using the chain rule, that's the same as d dx of h1 plus d dx of h2 is equal to 0. The derivative of h1 plus h2 is 0, then h1 plus h2 must be constant. We must have the solution h1 of x plus h2 of y is equal to a constant. So to recap, to solve a separable equation, we need to integrate m with respect to x, and we need to integrate n with respect to y, and then the solution is integral of m plus integral of n is equal to a constant, or we could write that integral of m is equal to minus integral of n plus c. But this is basically what we did last week when we separated the variables. Last week, the method I showed you was rearrange our equation so that all of the x terms are on the left, all of the y terms are on the right, and then integrate. In other words, we're integrating m and we're integrating n. We're basically doing the same method. We're integrating m and we're integrating n. So since we're basically doing the same thing, it doesn't matter which method we use. We could use the method from last week, or we could use this method. For example, solve the initial value problem. dy dx is 3x squared plus 4x plus 2 divided by 2, y minus 1, with the initial condition y is 0 is equal to minus 1. This differential equation is separable, and we can rearrange it so that all of the y terms are on the left and all of the x terms are on the right. Then we can integrate. Because the y terms and the x terms are separated, we're allowed to integrate, and we get y squared minus 2y is equal to x cubed plus 2x squared plus 2x, and then on the end, of course, we do plus c. Next, we need to find the constant c. I want to satisfy the initial condition y is 0 is equal to 1. You can check that if we put the numbers in, we get 1 plus 2 is equal to 0 plus 0 plus 0 plus c. So we find that c is equal to 3. So we could write the solution to the initial value problem in this form. Y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3. When we have a solution like this, where we have a function of y contained in our equation, this is called an implicit solution. Sometimes this is the best that we can do. For some examples you will see, the best type of solution we can get is an implicit solution. But for this particular example, we can do better than this. So in this example, it's possible to solve our implicit solution for y. In other words, we want to find y is equal to some function of x. This is what we want. Rearrange the equation. We find that we have y squared minus 2y minus this term. And this is a quadratic equation. Quadratic equation because we have something like ay squared plus by plus c is equal to 0. And we know how to solve quadratic equations. We find that there's 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. This is not a mistake, by the way. You can run through this calculation and you can check that we really do want plus 4 just here. This is one of the times that I'm going to say, please check. Please do this calculation and check that my solution is correct. Now, you'll note there's two solutions here. We have plus and we have minus. But only one of these solutions is correct. Which one satisfies if 0 is equal to minus 1? Well, we can check if we put x is 0, 0 plus 0 plus 0 plus 4. Then take the square root, we get 2. So we have 1 plus 2 or 1 minus 2. And this must be equal to minus 1. For this to be correct, we must minus, yes. So the solution to the initial value problem is 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. When I teach this lesson in a classroom, I pause and I ask the audience to answer it. Because I don't know if you're going to be typing the solution or not. I'm going to pause a moment and then tell you the solution. But please do try to go ahead and mentally answer my questions. You might type the answer in the chat or you might just keep it to yourself. Do have a think when I ask questions in these online classes. If we have a solution like the solution of the form y is equal to f of x, this is called an explicit solution. When possible, we prefer to have an explicit solution. Sometimes it's not possible to find an explicit solution and we can only give an implicit solution. This is a graph of this solution. You can see the graph starts at minus 2, passes through the condition 0, minus 1, and then continues. Notice that our solution is a differentiable function defined between minus 2 and infinity. Another example, solve dy dx is equal to y cos x divided by 1 plus 2y squared with the initial condition y of 0 is equal to 1. Let me run through this very quickly, and then when you re-watch this or read the lecture notes, you can check that this is correct. I'm rearranging the equation so that all of the y terms are on the left and all of the x terms are on the right, and then I'm integrating. I find that the natural logarithm of the absolute value of y plus y squared is equal to sine x plus c. And then to satisfy the initial condition, I find that I must have c equal to 1. So I obtain the implicit solution, natural logarithm of y plus y squared is equal to sine x plus 1. You can check this. For this example, it's not possible to find an explicit solution, so we finish on this implicit solution. But we might ask, what can we say about this solution? We can say that if y is equal to 0, the left-hand side is minus infinity, but the right-hand side is between 0 and 2. This means that y equal to 0 is not possible. Because we know that y is positive at least one point, that means that y must always be positive. Y is a differentiable function, in other words, y is continuous. If y is positive at one point and y is never 0, then y must always be positive. We can also say that the solution exists everywhere between minus infinity and infinity. In other words, for all values of x between minus infinity and infinity. But I'm going to leave this for you to prove. Our final topic for today is some differences between linear and nonlinear equations. For linear equations, we have a nice theorem. Some conditions first of all. Let's suppose P and G are continuous functions, at least on an open interval from alpha to beta, which contains the initial point t0. For y0, y0 can be any number. And the theorem says there exists a unique solution to this initial value problem with this linear differential equation. So that means as long as our functions p and g are continuous, the solution keeps existing. Or to say this another way, a solution can only stop existing when p or g has a discontinuity. For nonlinear equations, our theorem is not as powerful. This time, let's suppose a function f and the y derivative of f are continuous inside a rectangle. Here's a rectangle between alpha and beta and between gamma and delta. Let's suppose f and the y derivative are continuous inside this rectangle. And let's suppose our initial points t0 and y0 are also in these intervals, or to say the point t0, y0 is inside this rectangle. Then in some small interval between t0 minus h and t0 plus h, there exists a unique solution to this possibly nonlinear equation. This theorem says that only a little bit of the solution exists. In this blue rectangle, we know that f and the y derivative are continuous, but the theorem doesn't say that the solution exists everywhere in this blue rectangle. It only says that a very small part of the solution exists. Maybe the solution exists on the whole rectangle, we don't know. Maybe the solution exists outside of the rectangle, we don't know. all we know is that a very small piece of this rectangle, this solution exists. But that's enough to tell us that solutions of two first-order equations cannot intersect. If I drew two different solutions, and you will have seen earlier, it's possible for two solutions to come very close. That's okay. But what's not okay is for two solutions to intersect at some point. To understand why, let's suppose that they intersect at some point t0 and y0. But that's the same as saying that this initial value problem has two solutions. But the theorem says it's not possible. The theorem says this initial value problem only has one solution. So it's not possible for two first-order solutions to intersect. And just to be careful, assuming that f and df dy are continuous in this rectangle. And this is the end of today's lesson. There will be homework available later today. Previously, I've said that each homework would be available for 7 days, but I want to make a change to that. I'm worried that some students might register late for this course, or you might have technical issues. So I'm going to program in the system that each homework is available for you for the whole semester, which means that if you really wanted to, you could leave them all till January and solve them there. But I hope you don't do that. I would like you to solve one small homework each week to help you learn. But I'm not going to force you by setting the deadline each week. Do you have any questions? Okay, if you don't have any questions, you're welcome to leave whenever you wish. I'm going to take a 10-minute break and then I'll come back and see if there are any questions. If you leave and then you think of a question later, you can ask me on the discussion board and I'll answer it there. I will write the first homework later today and then you should receive an emailed announcement when it's available. Other than that, if you want to leave, you're welcome to, and I will see you next week.